course, welcome Haley. How are you? Welcome. DJ Roman, Haley, Cam's Lupian, Arvis. Chris A. Cool, man. Welcome to Weird Science. Athletic Man, what's up? Nirvana, what's going on? Welcome all. Welcome. This is Weird Science, and I'm your host, Mike F. Bell. A pleasure to see everybody here. Thank you so much for coming out. First, to get started, I wanted to show you what's going on with SpaceX. They launched another mission in the past week while we were in intermission between our episodes. I'm going to show that to you, so check out this. It's a SpaceX launch.
T-minus 30 seconds. All systems are go for launch, so let's listen into the terminal count and watch as Falcon 9 takes our stack of Starlink satellites into orbit. T-minus 15 seconds. 10, 9, 8, 7, 6, 5,
4, 3, 2, 1.
Ignition. And liftoff.
So this is another mission to deliver another batch of 60 Starlink satellites. It's like this is always... Hey, Kim. Oops, sorry.
At T plus 40 seconds into flight, Falcon 9 has...
No, what am I doing? Sorry. Hey, Sean.
At T plus 40 seconds into flight, Falcon 9 has successfully...
Adventure, what's up?
From Space Launch Complex 40 at Cape Canaveral Space Force Station, carrying our stack of Starlink satellites to orbit. Now we are
Starlink satellites, those are always good.
Max Q stands for
maximum aerodynamic pressure.
This is the largest structural load that the vehicle sees. Now, coming up in about a minute, we'll have 3 events.
Rin Higgs, what's going on?
The main engine cutoff, or MECO, stage separation, and SES-1, or second engine start one. Now, MECO is where all 9 of the M1D engines shut down
and then
vehicle down in preparation
for stage separation.
slows the vehicle down in preparation for the second event, stage separation.
Happy Weird Science Wednesday. Agreed. If you're just joining us, we're watching SpaceX put some Starlink satellites into orbit.
Will make its way back to Earth, while second stage continues on its journey with SES-1, or second engine start 1. And that's where we light up the MVAC engine, and it will propel the second stage along with the Starlink satellites to orbit. We're
Rebecca.
30 seconds away from those three events. Again, that is MECO, stage separation, and SES-1.
Yep.
We've got a really cool view of the first stage and those 9.
This is a replay.
engines burning bright.
But these are getting to the point where they're like very common. They're starting to happen so often. Like I'm beginning to play the same thing over and over again. But I don't want to give away any secrets, but the first stage does not make it. There we go. Second engine start.
And there you saw MECO and stage separation. On your left-hand screen is the first stage, with the right-hand screen being the second stage. And you can see SES-1.
Hey, what's going on? Thank you for the favorites.
Glowing bright red there.
I'm Mike F. Bell, and this is Weird Science. We're taking a look at SpaceX's Starlink, or SpaceX's Falcon 9 launching 60 Starlink satellites.
As a reminder, we will be attempting to recover the fairing halves today with our recovery ships Mystery and Mischief.
Thank you for the hot cocoa. Girth Brooks, where are you from? I am from Florida.
Will execute 2 burns in order to make its way back to Earth.
All right, let's go.
Entry burn. And that's where 3 of the 9 Merlin 1D engines will reignite.
Dolphin.
Help slow the vehicle down as it re-enters back into the Earth's atmosphere. The second burn for the first stage, second and final burn, is the landing burn. And this is where a single engine will reignite.
Thank you for the cherries.
Slow the vehicle down rapidly in order to touch down on that drone ship. Again, we are attempting to land on Of Course I Still Love You, and this will be the 6th
Of
attempt.
course, I still love you, and it's a fail. Stream Roller, what's going
On
on?
your screen is a live view of that second stage. This is the Merlin vacuum engine.
It's like spin those wheels. If you can spin those wheels, let's see if we can get that Kraken or the octopus or something.
In a vacuum.
So what's going on right now is that's the second stage right there. That's burning, and they're putting the 60 satellites into orbit, and
Just under a minute and a half away from the entry burn.
there's gonna be there's gonna be like 40,000 of those satellites by the end of at least SpaceX has applied with the FCC and FAA for like a whole bunch of satellites. It's gonna be really good.
Just 20 seconds or so after that landing burn has concluded, the second stage will have SECO.
I guess Mississippi 2 last night, but Ren is super cool. You gotta love it. Yeah, for sure. I can't believe I screwed up. I was like, oh, no. I thought I was going to win. I was overconfident. That's what happens. You get overconfident and hubris gets the best of you.
On a nominal trajectory. This is carrying our Starlink satellites to their targeted orbit.
Thank you.
We are just about 30 seconds away.
30 seconds
away from that entry burn starting up on the first stage.
Yeah, it's cool.
It lasts about 20 seconds long.
Like usually these missions go A-OK. They are actually trying to land the first stage, or they tried to land the first stage for the 6th time, but it did not work. Thank you for the favorites. Enter burn
You
startup.
can see on your left-hand screen as that view of
behind my head.
Those three engines are burning bright, helping to slow the vehicle down as it enters back into the Earth's atmosphere.
So that entry burn, and then what happens is they switch cameras for the landing burn, and it does not go as planned. It lights up, but you never see anything, so it obviously went into the sea.
Stage 2 is still looking nominal.
And welcome to Weird Science Wednesday. I'm Mike F. Bell, and we're talking about kinematics today. But first, we're looking at SpaceX's launch of another 60 Starlink satellites into orbit.
Just under 30 seconds away from the landing burn beginning on the first stage.
Thank you for the favorites. Just rocket science, no big deal. It's like this is all about conservation of energy and conservation of momentum. The principle behind rockets is that you're heating a gas up and expelling it out the back at a faster velocity than the rocket gas that was originally in there, and you're gaining it because you're gaining velocity because of Newton's third law. It's an object, or
no longer
see what happens here. It's lights all up, and then it kind of goes dark again. See some birds.
Right-hand screen
It's like,
stage 2 is still
probably go like this. Jump out of here for a second. You can't see anything. You're not going to see anything, so that doesn't matter. That was a fail.
Like we did not land our booster on a
Plunged into the sea.
It is
Oh well.
unfortunate that we did not recover this booster, but our second stage is still on.
Mike, what's up? What's going on? Big Dance
Earlier, that is second engine
DNYC.
Again, we are doing 2 burns for this MVAC engine.
We're taking a look at SpaceX here, and they're just launching some more satellites. So it's a good orbit, and from there I will go on to our next thing. So let's go ahead and bust into today's topic. Welcome, everybody. This is Weird Science, and I'm Mike F. Bell. First time here? Well, glad to see you. Thank you so much. So today we're going to talk a little bit about kinematics. What's that, you ask? It is the study of motion. So there's lots of things to do with motion and Newton's laws and all that kind of stuff. So what I have in this little picture next to me is just some of the equations of kinematics. It's just motion, like V equals V naught plus AT. Don't worry about any of this, because you know what? We're gonna learn some things and how velocity, acceleration, and position are related. So it should be a fun topic. And if you haven't had the chance to smash that favorite button, please do so. I really do appreciate it. And let's see here. On to the next. All right. So there's something that we can't go without talking about, and that is Newton. Because you know what? Alexander, or did I say Alexander? Isaac Newton. Isaac Newton, he was this guy up above my head. He invented calculus. He invented the laws of motion, and he figured out gravity. And I discussed him a little bit last week when I talked about gravity. But I hope that we could discuss him a little bit more, because I mean, this guy was a genius, and without him, we wouldn't be understanding things the way we understand them today. But anyway, he has what are called 3 laws of motion. Like, you probably heard them before, Newton's laws. It's like, so what are they? What are they? Okay, so let's just run through them. We got Newton's first law, and that is that an object at rest will stay at rest, and an object in motion will stay in motion unless acted upon by an external force. So what that means is it's just like inertia. It's like the tendency of a mass to stay in motion or not, or resist motion. So it's change in velocity. It resists change in velocity. That's what acceleration is. Okay, so the second law we got here is Newton's second law, and that is the sum of the forces is equal to mass times acceleration, right? Okay, so every force, your weight pushing down is a force, right? And that force is equal to mass times gravity. So it's your mass times the gravity. So you're not feeling any forces unless you're undergoing accelerations, whether those be accelerations or decelerations. So when you're in a car and you speed up and you're pushed into the back of your seat, that feeling is, yeah, goodbye, Pat Greggy. So you're getting pushed into the back of your seat. That is because you're undergoing an acceleration. When you stomp on the gas pedal or the accelerator, whatever it is, it's probably going to be just the accelerator. Nobody's going to call it the gas pedal once we all switch to electric cars. So that is an acceleration. You're feeling that force because Newton's second law, sum of the forces is equal to mass times acceleration. So the third law is that for every action, there's equal and opposite reactions. So that's basically conservation of force, conservation of momentum. And what I'm going to do is show you some examples of this. Okay. And one thing that we're going to talk about too is dilemma zones. Kinematics is the study of motion, like I said before. So if you want to figure out, okay, if you take something and it has a position. Okay, let's just go to an overhead camera. There we go. Here we go. So I got a couple of rails here with some Hot Wheels, because Hot Wheels are like really good for physics, and so are the Hot Wheels tracks. Okay, so if we look at this rail, I should probably extend this, sorry. There we go. Got a couple of rails here. And so the cool thing is that our position in time is able to be So, like, look at this car. This car starts here and then moves a certain distance, right? That distance covered is covered in a certain amount of time. So, what you have is a change in distance. So you start here at 0 and then go to here, which is, let's say, 100 in this case. And then that is actually, speed is different than velocity. This is velocity. Speed is a magnitude. And it's not directional. Velocity is a vector. So if you take this car and go from here to here, and you know the distance, and you just time it. All you have to do is time stuff. If you have a known distance and you time it, you're able to get the velocity really quickly. So you can get the velocity from that. And did you know that the change in acceleration, or the change in velocity, change of velocity is equal to acceleration? So what that means is that if you're just going along, just like cruising along at one constant velocity, that means that you're not accelerating or decelerating. Okay? So that means also, by Newton's second law, that there is... Thank you so much, all. And if you're watching, we are getting into some kinematics and Newtonian physics. I hope that I want to not oversimplify and not overcomplicate. So if anybody has questions, shoot them out. Unless you want to be a wise ass, which I totally encourage you to do, because my bouncers will get you. But our change in position versus our change in time. We have a known distance, and then we measure the time, and then we're able to get the velocity. And then if we take our velocity, we know it for a certain period, and then velocity somewhere else, and notice that there's a difference in velocity. That difference in velocity is what is called an acceleration. And accelerations are only something. So when an acceleration happens, you're feeling a force because of that second law. The sum of the forces is equal to mass, your mass, which is never changing, times that acceleration. So here, I have a track set up, actually. It's, here we go, another track here. And I've got some Hot Wheels cars. And you may remember from the other week when I talked about gravity and how all objects fall at the same speed, same velocity. And I had a feather, and I also had a ball bearing in a vacuum, and I showed that they dropped at the exact same speed. So as long as things are dropped from the same height, they will fall at 9.81 meters per second squared, or 32.4 pounds per feet squared, I think. No, in pound. I don't remember what it is in standard units, because we should be using SI. Anyway, so I'm going to let these cars go. They have two different masses. They're just two Hot Wheels cars, two different ones. They're different shapes, different masses, and when I let them go from my inclined ramp, that didn't work. Gotta actually make sure I let them go at the same time. There we go. They go and hit exactly the same time. Yeah, you would think that. You would think that, but they go exactly the same time, and they have to because that one didn't because I let it go weird. But when I let it go correctly, they hit at the same time, and that is because gravity is acting the same on everything. Every single thing is getting affected by gravity the exact same way. And welcome, everybody. This is Weird Science, and I'm your host, Mike F. Bell. Today, we're talking about kinematics and, yeah, for sure. Talking about kinematics and Newtonian physics. So strap on in and smash that favorite button if you haven't had a chance. Okay, so something that I wanted to show you guys too is that, hold on. Okay, so I have some objects. This is just a little ball, and this is a cylinder weight. And when I put this up here and I let them go, they'll actually hit at the same time. Ah! But anyway, they hit at the exact same time. It's a pretty cool thing. And the nice thing about kinematics is it's very, very describable, and you could follow it. And when you know positions of things and you measure out the distances involved, you could find the numbers that you could find accelerations, you could find velocities, you could find everything. Like, it's really neat, all the stuff that you could do. Okay, so the one thing is conservation of energy and momentum. You've probably all seen the example with the Newton's cradle and the balls that are suspended from, hung from, and they are in a line, and then, yeah. So what this is kind of similar. Watch this. So I'm going to hold this here steady. I'm going to take this car back and slam it into this, and you'll see the other car. Look at that. And that's because conservation of momentum, because what's going on there is you have a mass, M1, and you have a velocity, V1, right? So M1 V1 is equal to M2 V, or M1 V2. Yeah. So what's going on is, here, I do it again. Just put a bunch of cars in line. Whoops. Whoops. It's like that one has a little bit of a steep slope and jumped up. Bam! Look at that. It's pretty awesome. Yes, please do spin those wheels to show some support. If you guys are just joining, say one, or actually put a one in the box, or one in the comments. Thank you, Rebecca. So when a boxer punches and connects with another boxer's head, that force momentum will carry on through the head. Exactly. Because that has to go somewhere, because there's conservation of momentum and conservation of energy. And that's 100% true always in the environment. Sean. No, yeah. Okay. So what's cool too is with that same ramp, I could actually roll like other stuff down it, and it'll like go down at the same speed. Yeah, so that was a ball. And the weird thing too is unfortunately I don't have the hoops set up, because hoops actually roll differently than spheres and than discs because of inertia properties. It's a lot of things are based on inertia. So I have another toy here. Okay. So I have this ball on top of this cart, and I roll it, right? As long as there's not an acceleration, as long as my acceleration is equal or close to zero, that ball doesn't fall off. Okay? So, like, see, I can move that without that ball. But if I'm to accelerate that fast, the ball falls right off. That's because an object in motion stays in motion, and an object at rest stays at rest. So when things are moving around, as long as they're not accelerating, you won't notice it. For instance, we are spinning very, very fast. We're going like 17,500 miles per hour, at least around our Earth. And on top of that, we're going very fast around our sun. And our sun is moving around our galaxy. So we're actually kind of like we're moving very, 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 very rapidly through space. But it's all about relative velocities. So even though we're moving very fast, our velocity compared to the velocity of Earth and everything is the same, and there's no acceleration. If we were feeling an acceleration, we would die for sure, without a doubt. So it's accelerations that are very important. Accelerations are responsible for forces, and you can't have the forces without those accelerations going on, because by Newton's second law, you got the sum of the forces is equal to mass times acceleration. So, like, I hope this is kind of making sense to you guys, and you're understanding the topic. If you do have questions, like, feel free to chime in, And thank you so much. Baby GG, what's up? And what's up? Thank you for the favorite. I appreciate that. I'm not allowed to do that, so we will not be making any. I am sorry about that. Streamroller. So you may notice too that like when you go into a turn, that you feel yourself being pulled to the side, and that's because of the centrifugal force. And there's two forces. There's the centrifugal force and the centripetal force, which acts in the opposite direction. So when you're going around a turn, it's actually causing you to go through an acceleration because the acceleration is v squared over v over r squared. So is acceleration a vector? Yes, it is. Acceleration is a vector, as with velocity. Velocity is a vector. So those have little arrows on the top of them. You may or may have seen them if you've done some more advanced math. Yeah, v divided by r squared. Yeah. Streamroller. That's why you have to press the gas in boats to turn. So don't drop a bowling ball out of a moving car or it will flatten. Yeah, because when you drop a bowling ball out of a car, it's going whatever velocity you're going at that time that you dropped it. So if you're going 60 miles per hour, that ball is going 60 miles per hour. The only acceleration that it's undergoing is the acceleration from gravity. So that's downwards. Yeah, it's the same velocity as the car. So that's kind of like another thought experiment. When you're in a car, when you're driving along, and let's say you have the cruise control set, so you're going a constant velocity. A constant velocity means your acceleration is zero, equal to zero. So what happens? Okay, you're driving your car, you have the cruise control set, and you have some item, and you drop it. You just drop it. What will happen? Will it go straight back? Will it fall straight down? Will it go forward, left, right? I don't know what. Straight down, exactly. It would go straight down, and that's because that ball is going the same speed as the car, despite what you're thinking. Like, the ball isn't undergoing any acceleration, so no change in velocity, so no acceleration. Thank you. And if you're just joining me, this is Weird Science, and I'm Mike F. Bell. I hope you are having a good time and learn a little bit about kinematics and Newtonian physics. It's just some cool stuff to think about because, you know what? You could actually look at your time and look at your position. Top view. So you're moving, going along. But if you approach that stoplight and that changes and you're going too fast for you to safely stop, you could argue that it was safer for you to run the red light than it was for you to stop. Feel like it would have caused me to undergo a dangerous deceleration, because what is a deceleration? It's a negative change in velocity. So that change of velocity over change in time. Remember, that's the acceleration. When you have a negative change in velocity over change in time, it's a deceleration. And that's slowing you down. So if you get to a certain deceleration, it would be not safe to stop that hard. And it could be argued very easily. I've actually won in court just going there like several times. Like, you can't mess with the scientist. You would have to be going pretty darn fast. Stop running red lights. I know you have. Several times. Hey, there is nothing wrong with using science. And how is everybody? Welcome to the stream. This is Weird Science, and I'm your host, Mike F. Bell. We are talking about kinematics and Newtonian physics today, so I hope you are understanding this and learn a little something. So one thing that we can't forget about, too, is that Newton's first law. It's all about inertia. You're welcome, Rebecca. I'm glad that you learned something. And Kim, I hope that you learned something as well. I hope that I was able to break it down, especially because you're doing this in your class. I always learn something on Wednesday. It's great. Thank you so much. Did I miss everything? Yep, got to be here at 3 p.m. Eastern sharp. That's when I kick off and things get going. And just so you all know, Emoji J is recording this episode, so be sure to favorite him on YouTube, follow him in YouTube, and you could see the episodes. So be sure to check it out that way. Don't let the apple hit you on the head. Yeah, because you know what? Gravity. But the thing with gravity is we covered that last week. So the last week's episode, we talked about how all things fall at the same rate, regardless of their weight. And this week, we showed you how two objects rolling down an inclined plane are going to roll the same speed, regardless of their mass. So we have a inclined plane over here, and you're able to see, hopefully, this, that if I have these two cars and I put them up here at the top of this ramp and then let go. Oops, I didn't let those go at the exact same time. Girl the boss, pleasure to see you. How are you? Good to see you. We're just doing a little demonstrations and stuff. And I was talking about the conservation of momentum. And here I have a track set up. So watch what happens when you have the collision. It will transfer just like a Newton's cradle. So watch. See, it went right through. It's like, And watch, if I hold it in a different spot and make these cars crash together, watch what happens. So, like, if I hold this one right here and then slam this car into it, watch. Oh. It makes that one go. It's just like a Newton's cradle, which is the device with the bearings suspended and it looks together. Science is totally cool. Must ask you a question. Go ahead. What's that question? Let's go. Let's go. It's like, hopefully it is science related. This is cool. Appreciate that. I have heard about Eflux city with similar. I'm not sure what you're asking. And if you are, this is your first time here, make sure you smash that favorite button. I really want to get favorites, as many favorites as possible. I'm getting closer to 4,000. Oh man, oh man, oh man. Smash those favorites if you haven't done so already. Thank you for the favorites. Kit Kat. I appreciate that. Everybody, smash those favorites. Let's get those favorites to 4,000. And we are talking about conservation of momentum, Newton's laws of motion, and kinematics all rolled into one. So please do Newton's cradle. I would do a Newton's cradle, but I actually broke it, so we're not doing Newton's cradle. It's like I'll have to set it up. I'm thinking about making a big Newton's cradle with billiard balls. So that would be cool. And then an Euler disc would be another cool thing to show. I think Euler discs and also gyros are pretty cool. There's a lot of stuff with like angular momentum. Thank you for the favorite. Yeah, gyroscopes are neat. Like the International Space Station actually uses gyroscopes to control its orbit. Because you could actually, they have this giant rotating disc and it has lots of inertia. And it's spinning really, really fast. And that inertia is just staying there spinning at the same speed because there's no acceleration until you speed it up or slow it down. Yeah, gyroscope's ability is really cool. I like putting vodka in a plastic. And then I check it. Makes a lot better. That's funny. Yeah, it's just vapor pressure of the vodka. You probably just like heating up inside the bottle, like, and then that hitting onto the ground is enough to just like, yeah, you sound very annoying. I would hate to have you as a neighbor. Not gonna lie. Well, I would love to have you as a neighbor if you played guitar all the time, but if you were blowing stuff up, I probably wouldn't want to have you as a neighbor. And go ahead and smash that favorite button if you haven't done so. because we're getting really, 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 very close to 4,000 favorites. Trophy Mail, what's up? Non-Newtonian fluids are also an interesting area. I agree with that. Non-Newtonian fluids like corn, starch, and water that acts like a non-Newtonian fluid. Silly putty is a non-Newtonian fluid. Anything that just doesn't act like water is pretty much a non-Newtonian fluid. Thank you for the favorite, Catherine. Hi, how are you? Ding. Ring ding dong. Ring a ding 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 dong. And I am okay. Snap me. Good to see you. Aloha. Let's get ready to rumble. Exactly. And make sure that you stay up to date with all my latest news and info about the show. Go and favorite me on Instagram. Same username as here, Mike F. Bell. So if you don't follow me on Instagram, you totally should. I post other content and I post experiments sometimes. So you should totally check out my Instagram. What is today's experiment? You missed it. It's like my time slot is from 3 to 4, so I gotta run a tight ship. So be sure to follow me and come next week at 3 p.m. Eastern, 12 p.m. Pacific time for Weird Science. Thank you for the favorite, Nada. Thank you for the favorite, Queen. You got done with the workout late. Well, next week you gotta work out sooner or work out afterwards because you gotta come by. It's a Weird Science. What's your stand on laminar flow as a perfect flow? Is that really perfect? I'm not going to go into that here, Rohan. You sound cool and you sound like you're an engineer, but I'm not going to go into here. I found someone said only once a week. Yes, once a week I do this, and I also do. They won't put you on the TV instead of stupid CNN. Yeah, I should be on the TV. I should totally be on the TV because, I mean, when you're awesome. This is pretty cool, man. I'll see you next week. What did you miss? You missed the show. I hope that you're going to be able to turn out next week. Thank you for the favorite. See me. Your formula for life is fantastic. I agree. ID cast you from Mathu. Check you out next time for sure. Next time is next Wednesday at 3 p.m. Eastern, 12 p.m. Pacific time. So basically next week, but an hour earlier than now. Thank you for the favorite, Kaz. I see Hot Wheels cars. Yes, because I was everything can be shown with Hot Wheels cars. It's like, look at this, conservation of momentum. And it's like a Newton's cradle. An object in motion stays in motion, and an object at rest stays in rest. It's like, here's another, toys are great for demonstrating physics. It's all about demonstrating. Girl the boss. Woo, thank you. And let's get those favorites to 4,000. Come on, guys. Smash those favorites. We need a way to watch repeat. I happen to study chaos theory and QED. What's going on, Trophy? The show will be on Emoji J's YouTube channel. Yes, it will. I am also recording it. I'm working on getting my YouTube channel. Unfortunately, when I make videos for this, they don't record and transfer really well to YouTube because of the different aspect ratio. I do. I screen record everything and make sure everybody screens record. Because you never know. If your guy's going to spin those wheels, let's see if we get that cracking. Favorite me, and I will be sure to send out blast. What does QED mean? Para Edra Fan, I don't remember exactly. QED is what they put at the end of the paper. Like, it's like, this is proof. QED. It's like, here's my proof. It's kind of like a douchey thing to like. Well, quantum electrodynamics? No. Sorry. You're wrong. QED is what people put after like a solution. Like it's like what's going on, Cuddy? How are you, sir? Pleasure to see you and welcome to the show. I am wrapping up and this is the end. I will be getting off here very soon. Yes, it is the Science Channel. Demonstration of conservation of momentum with included demo of impulse theorem will be very interesting. It's like I was thinking about making something to show like impulse and snack, crackle, and pop, jerk, and yeah, I can't remember. So thank you for the favorite. And Johnny Boy, how are you? Let's get those favorites up. We got 40 more and we're going to be hitting... Every time someone favorites you, do the ring the bell. Yeah, I'm trying to do that so I could get more people to favor me. Come on, favor me and I'll ring the bell. Goldfish, thank you. Fantastic, thank you. Yep, come on, let's get those favorites up. Let's get those 39.61. We got 39 to go. Ding, ding. Play the song. You could ring my bell. Your bell. I love science so much. Science is my life. It's mine too. Faster than light. Are you going to question me on everything there, Vita? I'm probably got more knowledge in the tip of my thumb than you have. Exotic! How far is it from here to the sun? It is 93 million miles. 93 million miles to the sun. It's about 8 seconds to get to the sun for light. Faster than light. And who knows if faster than light is actually possible. According to Einstein, it's not. You can't go faster than the speed of light. 8 minutes. Yep, you got it. Thank you for the favorite, Mr. Maybe. Why do photons not know where they are going when passing? That's what I said, 8 minutes, right? Why can you not trust an atom? Can I dance on the sun? If you want to die, probably. Yeah, not 8 seconds, 8 minutes. Lysol, it's... I am. Elon Musk is awesome. It's like, I think that he should totally hire me to go work at SpaceX. Yes, I totally appreciate science jokes. Oh, look at that. An astronaut for the European Space Agency. Cool. My next experiment will be find a way to capture CO2. Yes, if I could find that, it's worth lots of money. But it makes me wonder because Elon Musk invested 1.5 billion in Bitcoin, but Bitcoin is kind of like a very energy intensive thing to mine. So I'm not sure how environmentally friendly that was. He'll pay you. How small is? I will create Elon clone and call it Musk. Bitcoin working is very complicated. Yeah, I agree. I totally agree with that. Well, it looks like I am very, very near to the end of my time. I totally appreciate everybody coming in and hanging out and learning a little bit of science. I hope that today I was able to show you how dynamic motion and kinematics and Newtonian motion is everywhere. I explained a little bit about how position and time you could find your velocity. And change in position is change in position over change in time is velocity. Change in velocity over change in time is acceleration. Acceleration is responsible for creating forces because the sum of the forces is equal to mass times acceleration. And remember that Newton's first law, an object in motion stays in motion and an object at rest stays at rest. That's because of inertia. Inertia is based on mass and it's an object's resistance to change. And I appreciate everybody coming in here. And finally, we talked about Newton's third law. And for every action, there is an equal and opposite reaction. And thank you for the favorite, Sarah. Thank you for the favorite, Vita. But hopefully you all learned a little something and had a good time doing it. thank you all so much. I will be ending my stream in just a minute. Hit that favorite, smash those favorites, smash those hearts, smash those diamonds. Let's go, guys. Let's go, let's go. There we go. That's the 11 bell salute. It's like you're welcome. And thank you all so much for joining me. I will see you next week. Be sure to tune in next Wednesday, 3 p.m. Eastern, 12 p.m. Pacific time. I will see you guys next time. Thank you so much and have a great night. Bye.